Okay, video 6.2 of soil water retention and movement includes a discussion of soil water infiltration and the effect of texture, porosity, and structure on infiltration rates. And this is important for this week's lab because there's going to be a demonstration on infiltration. So infiltration is basically the rate at which water enters a soil and moves through it. And you can see that in a coarse textured soil, it should be very rapid. And in a fine textured soil, because there's smaller particles and smaller pores, the rate is slower. And part of this is because there's smaller pores, they have to displace air. So if we imagine that this is the soil surface and we have precipitation falling on this soil surface, and we have pore in a fairly dry soil, we have air that's got to be removed from the pores, and then water can infiltrate the pore space and can flow vertically down the profile. And the movement of water in the profile is called hydraulic conductivity. And what we'll see on the next video is that hydraulic conductivity is a function of the rate of infiltration. We can define infiltration rate as infiltration, or I, is equal to Q divided by A and T. And Q is a soil property that varies with texture, structure, and porosity. And A is the area of soil that water is being applied to, and T is time. So we'll just spend a few minutes discussing the idea of particle size, surface area, and porosity. And we'll do that using this generalized schematic. And basically, I want you to consider these in 3 dimensions. I'm only showing you this in 2 dimensions, but really you have to consider that this is a 3-dimensional object, and these spheres are in 3 dimensions, okay? And so that in this cube has a side length of 16 millimeters. Then each one of these circles has a diameter of 8 millimeters and a radius, therefore, of 4 millimeters. So that would be considered a large particle. And remember that in the cube, so we have, these are solid spaces. So the blue is represented to be solid, and the green is the empty space inside this cube, and these are the pores. Okay, and we're going to consider 3 different particle sizes. We're going to consider a large particle size, an intermediate, and a very small particle size. So in this case, we have 16 millimeters across. 16 millimeters across here. We have 1, 2, 3, 4, 5, 6, 7, 8 of these. So each diameter is 2 millimeters. So the radius of these particles is 1 millimeter. And if we count up, if we multiply the number of these, then we have 2 by 2 by 2. We have 8 particles in this 16 millimeter cube square. Versus we have 8 by 8 by 8, 512 of these smaller particles in this 60 millimeter length, width, and height cube. So we can look at some calculations on the next page to calculate the amount of surface area and the total volume and the pore space. And so if we remember, that the cubic volume is equal to length times height times width. And so for that example on the previous slide, we had 16 times 16 times 16 is equal to 4,096 millimeters cubed. And I said we're going to consider 4 examples. So we had the radius of a large particle, a medium particle, and a very small particle, 4, 2, and 1. So we can calculate the surface area of a sphere as equal to 4 pi r squared. And so if we can calculate the surface area of these 3 different size particles, we get 201 50 and roughly 13 for each of these. Okay, so we got 201 millimeters squared of surface area for each individual particle. 50 for each individual particle of the 2 millimeter radius, and 13 millimeters squared for each individual particle of the 1 millimeter radius. We can calculate volume as equal to 4/3 pi r cubed. So therefore, for each individual particle, we get 268 millimeters cubed. For the large particles, we get 34 millimeters cubed for the medium-sized particles, and 4 millimeters cubed for the small ones. And then we have the number of particles. So as we saw, we calculated we had 8 particles here. If the particles are 4 millimeters in diameter, in this volume, in this cubic volume here, we would have 64 of those. And from the small particles, 2 millimeters in diameter, we had 512 of those. So we can multiply 8 by 201 to get the total surface area. And that comes out to 1608. For the 2 millimeter radius particles, the medium-sized particles, we get 3216 millimeters squared of surface area. And for the smallest ones, we get 6,433 millimeters squared of surface area. So you can see that, and this is something I said in module 1, that as particle size decreases, surface area increases. We can calculate the total volume of these, and this is interesting. The total volume ends up being the same for all particle sizes. The only difference is if you're not carrying the decimal places or not using all the decimal places, but they're basically the same. And so if we subtract, so that's the total volume of particles. So if we subtract, if we're looking for in this cube, in this known area, and we're looking for the total pore space, we subtract the total volume by the particle volume, right? So pore space would equal total volume minus solid volume. We get the same for all of them, 1952, 1952, and 1951. And you can go ahead and check the calculations here, but the reason for this is that so we saw that there's higher surface area with smaller particles. We would expect there to be, based on some of the lectures we've had so far, that the amount of porosity would also be larger, but the porosity is the same based on particle size until we get secondary aggregation of those particles. And once we get aggregation into macro, meso, and micro aggregates, and we get a variability of distribution, then we get changes in pore space. And also, because all soils are a mixture of particle sizes, then we get differences in porosity across soils. And so this is the influence of texture and structure on pore distribution and therefore available water content. And so we'll define a couple different sizes of pores. We can have macro pores, or these can also be called transmission pores, and they are greater than 50 microns in size, and these are drained at field capacity. We can have mesopores, or another word is storage. These are between 0.5 and 50 microns in size, and these represent the available water holding capacity of soils. And then we can have micro or residual pores, and these are less than 0.5 microns in size, and these represent mostly unavailable water. And so what we can see is that different textures have a different distribution of these. And so we have fine and coarse pores, but what we'll do is we'll sort of say that here's where our mesopores are in this range here, and then we have mesopores are in the middle. And what we can see is that the distribution of mesopores is highest here in the loam soil, and that's where the available water is. And so in a fine texture soil, we have a lot of fine pore space that would be residual and so unavailable, and we have a little bit of macro pore space which drains right rapidly. But our available water is not necessarily as high as in the loam texture, which is dominated by these storage pores, versus our sand, which is dominated probably by these macro size pores. And therefore water drains out of sands rapidly, and there's less of this available water in the middle. The last slide for this video is just this idea of the influence of structure on water infiltration rates. And so we can see that if we have granular structure, we have very rapid flow rate. If we have a blocky structure, we get a moderate flow rate. If we have prismatic or columnar, we get a moderate flow rate. And if we have platy structure, we get a very slow rate. The granular is rapid because you have small round PEDs. It's easy for water to flow around. Blocky is sort of moderate because you have angular PEDs, inhibit drainage a little bit. Prism is typical of our high salt content soils, and therefore these now have the influence of osmotic potential, and it slows down the flow of water. And platy, we have these horizontal PEDs inhibiting vertical flow.